Continuing on with tools of geometry, we're going to look at points, lines, and planes. Now, a point is the only term in geometry that we cannot give a definition for. The reason why is because points don't have any dimension. There's no depth, there's no width, and there's no height. When you write a point on your paper or as part of an answer, remember that a point is always going to be represented by a capital letter. Then we look at lines. A line is represented by a straight path that extends in two opposite directions without an end, but it has no thickness. A line contains infinitely many points. So when we think of a line, it's always going to be first dimension. It has width, but it doesn't have any height, and it doesn't have any depth. When we name a point, we're always going to use two capital letters that are on the line, 2 points that are on the line to name that point. Another thing that you want to remember about lines is that they go on indefinitely. They're infinite in both directions. Finally, we have planes. A plane is represented by a flat surface that extends without end and has no thickness. A plane contains infinitely many lines. So a plane is going to be 2 dimensions. It has height, it has width, but it doesn't have any depth whatsoever. And actually, the height and the width go on infinitely as well. When you draw a plane, or when we represent planes on paper, we're going to use either a rhombus or a parallelogram to represent any planes that we have. Now, moving on to problem number 1, we're looking at naming points, lines, and planes. And the first question is, what are 2 other ways to name line QT? Now you can see that we have plane P. The reason why we're going to call this plane P is because we have a capital P down in the bottom left-hand corner of that plane. We could also name the plane with any 3 letters that are inside of that plane, or any 3 points that are inside of that plane. So any combination of V, R, Q, S, or W. But the question is asking us to focus on line QT. So what you first do is identify where is Q and T. The line that contains Q and T is the one that is going vertically. We need to ask ourselves, does the line have a name? Are there any other points on the line? Now, the answer to the question, does the line have a name? Yes, if we look down at the very bottom, you're going to see an italicized M. So we can also call this line M, as well as line QT. You're also going to see that there's another point on that line. So we can combine Q and T within any combination of those 3 letters, and we can name that line. So our solutions are going to be line M, line QN, line NQ, line TQ. Any of those are going to be correct responses for that. The second question that we need to answer is, what are 2 other ways to name plane P? And as I said earlier, since we've got several letters on that plane, we can choose any 3 in combination as long as they're not what we call collinear. So we can't choose R, Q, and S because they're collinear. You can see that they're all in line K. But we could choose R, V, and Q, and that would be plane RVQ. You could also say plane QVR, plane VQR, plane RWS. Any combination of those letters will work to name that plane. The third question, what are the names of 3 collinear points? So we do have 2 sets of collinear points here. We have R, Q, and S, and we have T, Q, and N. And then what are the names of 4 coplanar points? Any combination of R, V, Q, S, and W. Or you could say T, Q, N, and then any of the other letters that are on there. Or you could say R, Q, S, and then any of the other letters that are on there. And all of those would also be coplanar. Before we get to problem 2, we need to take a look at 3 more terms. The first term is a segment. Now, a segment is a part of a line that consists of 2 endpoints and all the points between them. So if we go back to the line that we had in the last problem, line QT. If we wanted to make a segment out of that, we would take all of the points up to and including Q and T that are in between Q and T. If we're going to name a segment, then what we're going to do is we're going to use a line above Q and T, or a line above whatever two letters we have, but there are not going to be any arrows on the ends of those, on the end of that line. The next thing we have is array. Array is a part of a line that consists of one endpoint and all the points of the line on one side of the endpoint. So again, if we were looking at array QT, what that would mean is that our array starts at Q and then goes in the direction of T and passes through T and continues on. If we were to say array TQ, then it would be array that starts at T, goes towards Q and passes through Q and continues on to infinity. The third term that we need to look at is opposite rays. Opposite rays are two rays that share the same endpoint and form a line. So if we're looking at the last example where we had N, Q, and T were all collinear, then Q being the center point, we could make opposite rays using QT, ray QT, and ray QN. Since Q is the starting point for both rays and they're going in opposite directions, that would consist of opposite rays, or that would comprise opposite rays. Now in problem number 2, we're looking at naming segments and rays. And the first problem that we're going to solve is, what are the names of the segments in the figure that we see here? So we have points D, E, and F, which are collinear. And we want to look at how are segments named, which is, again, 2 points. So we can say segment DE, we can say segment EF, or we can say segment DF. All three of those segments are correct answers for this question. It doesn't matter which direction we go in, so we could switch it around and we could say segment ED, segment FE, and segment FD. Those three segments are the same segments that we named earlier when we said DE, EF, and DF. The next question that we want to answer are, what are the names of the rays? So in this situation, we can start at point D, and we could say ray DE. We could also say ray DF. Now in reality, ray DE and ray DF, since they're collinear, would be the exact same ray. Moving on to E, we could say ray ED, which is a ray that starts at E and then moves to the left. Or we could say ray EF, which is a ray that starts at E and then moves to the right. Ray ED and ray EF would be opposite rays. And then we could also do rays starting at F, which would be ray FE and ray FD. And again, ray FE and ray FD would actually be the same ray, simply because they're collinear points to begin with. And again, which of the rays in part B are opposite rays? Ray ED and ray EF. Now we move on to our first postulate. Now a postulate is an accepted statement of fact. Postulates may also be called axioms, but in this book we're going to refer to them as postulates. And postulate 1-1 is, through any 2 points there is exactly one line. So this is something that is always true. And as you can see on here, we have points A and B. You can only draw one line through points A and B. Now, later on in the year, you're going to have to do something called proofs, in which you explain how you arrived at an answer using all the proofs and theorems and postulates and everything that we've got. And you're going to explain how you got to a specific answer. Any postulate that doesn't have a specific name, in this case, it's just a numbered postulate, 1-1. You don't have to remember the numbered postulates, but any postulate that has a name, something like the segment addition postulate, you'd have to remember that and be able to write that down later on. That moves us on to postulate number 1-2. And in postulate 1-2, we know that two distinct lines intersect at exactly one point. So on this graph here, you can see that we've got two lines, line BD and line AE. And as long as they are not parallel, and as long as they're not in different planes, then they're going to intersect at exactly one point. So again, that's postulate 1, 2. Now, again, you won't have to remember postulate 1, 1 and postulate 1, 2, but you do need to know how to apply them. So even though you don't need to know that the rule matches up to 1, 1 or 1, 2 or 1, 3 or whatever, you still have to be able to apply whatever it is that we've talked about. That brings us to postulate 1, 3. If two distinct planes intersect, then they intersect in exactly one line. So again, these are planes that are not parallel. These are planes that are not sitting right on top of each other. We're talking about planes that do have an intersection. And anytime that planes intersect, the plane is always going to intersect in a line. As you can see on this example, line ST is the intersection points of those two planes. As we move into problem number 3, we're going to be looking at finding the intersection of two planes. So the question is, each surface of the cube represents part of a plane. What is the intersection of plane ADC and plane BFG? So the first thing that you want to do is find plane ADC. Plane ADC is the top face of that cube. Now remember that when we're talking about planes, they're not confined to a specific area. They're going on infinitely in all directions. So what we're looking at is just a kind of taking the planes and taking them and putting them into a cube form. But just remember that those planes would move out to infinity. And the lines would also be infinite as well. They would not be segments. The next thing we're going to do is find plane BFG. Now you can see that plane BFG from our perspective is the right face. So we have an intersection of the top face and the right face. On which line do these intersect? They intersect on line BC. And now we're moving on to postulate 1, 4, which is something that we've already talked about a little bit in a previous question. Through any three non-collinear points, there is exactly one plane. So in this illustration, you can see that R, Q, and S are three separate points, and all 3 points are non-collinear. Since those 3 points are non-collinear, there's exactly one plane that will intersect all 3 of those points. In problem number 4, we are given, the first question is, what plane contains points N, P, and Q, and we're asked to shade the plane. So the first thing that we do is we locate the 3 points of N, P, and Q. Those are on the bottom edges of the cube. The next thing we do is we shade the face. So we would shade the entire bottom face, and we can see that NPQR is the plane that we're looking for. The next part of the problem asks us to shade the points or describe the plane that contains points J, M, and Q. And we're going to shade that plane. So J, M, and Q, you can see they're not on the face, they're not all on one face of the cube. This is permissible, this is possible. Remember that through any 3 non-collinear points, there is exactly one plane that intersects all 3 of them. So what we have to do is we have to draw in what is that plane going to be. So if we draw in that plane, we can see that it's going to be a tilted plane. It's going to go from the upper left-hand corner of the cube down to the bottom right edge of the cube. And that is going to be our plane.